Hi, welcome back to STEM Builders JM. I'm Cavell Hilton, Chief STEM Ambassador, and today I have a very special presentation for you by Miss Gabrielle MacLeod, one of the very few physics teachers, female physics teachers in Jamaica. And she'll be assisting all the CSEC students to get excellent grades in their exam. So please let Miss Gabrielle MacLeod feel welcome. Hi, Miss MacLeod.
Excited to be here. All right, so hi everyone. I will be speaking to you guys today about the physics of the atom, and I'll just be running through a few topics with you, the first of which I'm going to show you in this outline. So give me 1 minute to just bring up the screen, and here we are. All right, so today we'll be running through the history of the evolution of the model of the atomic structure, the modern view of the atom, nuclei representation, isotopes, radiation, including alpha, beta, and gamma radiation, and also the concept of half-life. All right, so Sir J.J. Thomson discovered the electron in 1897, and before this, what they thought that atoms were the smallest, most indivisible piece of matter. So J.J. Thomson would have come about and he found evidence that pointed to electrons or cathode rays that were basically fired from every single element. So because he realized that there could be particles that are smaller than matter, then he concluded that these atoms were called, or these particles were referred to as electrons. So in finding these smaller particles, what he realized was that the shape of the atom could be put in a certain context, and he referred to this model as the plum pudding model, which he developed in 1907. Now what that plum pudding model looked like, it was a sphere of positive charge. As you can see, there is a red background here, and the negatively charged smaller particles, which were referred to as the electrons, were scattered inside the model. And so you see that it's kind of looking like an actual pudding, which is why he would have called it the plum pudding model. All right, so the next scientist we're going to be looking at is Sir Ernest Rutherford and his two students, Hans Geiger and Ernest Marsden. Now, Rutherford was the lecturer of Geiger and Marsden, and he had fired some alpha particles at Michael and realized that most of the particles passed straight through the film, meaning that no holes were made. So can you imagine you fire some peas through a piece of paper and the peas just pass straight through the paper, they don't make any holes at all. And so he was pretty much dumbfounded by this, and he realized that a few of them were actually deflected. So this led him to a new proposal of the form of the atom. He said that the atom would have to be a structure that contained a very small central nucleus where the majority of the structure was actually just empty space, because if the particles were flying straight through, they had to be flying through empty space because they weren't meeting upon any diversions. All right, so Hans and Geiger, who were his students, they set up an experiment where they fired alpha particles at a thin metal sheet. And upon firing them, they realized that some of them actually backfired towards them. And so they ran to their teacher and they said, "Sir, there is something very weird that is happening." And he said to them, "This seems so unreal. That would be almost like if I fired an M16 at a piece of toilet paper and just imagine that the bullet started ricocheting back to you." And so his hypothesis was actually true. Most of the atom is concentrated in a centralized electrically charged nucleus, and the majority of the atom is actually empty space. All right, so we're going to look at another scientist, that's James Chadwick. Now, Chadwick found evidence that pointed towards the existence of a neutron, a particle that is slightly larger than a proton with no charge found in the nucleus. It is known to exist as a basic constituent of matter. All right, so now that we have had all of these scientists putting their views together, we're going to use those to put together what we now view as the modern structure of the atom. So our modern view of the atom is that it consists of positively charged nuclei. Okay, so our modern view of the atom is that it consists of a positively charged nucleus and it is surrounded by electrons. Now, inside the nucleus, we would have had protons and neutrons. And so the equal amounts of charges from the electrons on the outside and the protons on the inside would have led to our atom having a neutral charge. That means it is not charged. So together they make up most of the mass of the atom, but they occupy only a very small percentage of its total volume. And the electrons, which occupy most of the volume, constitute only a tiny percentage of the mass. So if you look at this diagram here, you'll see where it's pointing towards a central nucleus. Now that nucleus is very, very tiny. In fact, it is in the range of 10 to the minus 4 angstrom. Now, angstrom is the unit that's used to measure very, very small distances. And the outside here is the majority of the space of the atom, but it is mainly empty space because the electrons are suspended there. Okay, so we're going to be looking at nuclide representation now. The number of protons in a nucleus is denoted by Z, and we call this Z the atomic number. The number of neutrons is denoted by N, and that's referred to as the neutron number. The total number of nucleons in a nucleus is denoted by A, which is the total number of protons and neutrons, and we refer to this as the mass number. Now, if we add together the atomic number and the neutron number, then we should get back the atom's mass number. So having a closer look at this, we'll realize that the symbol X here is the chemical symbol for the element. The mass number is in the superscript, that is A is equal to Z plus N. And the atomic number is the number of the protons represented in the subscript here as Z. Now, if we wanted the neutron number, what we would have to do is to minus the number of protons from the mass number in order to get the neutron number. Okay, so let's run into isotopes. An atom is normally neutral, as we would have said before, because the number of protons is equal to the number of electrons. And so because it is in a neutral state, it must possess the same amount of protons as electrons. That is a cancellation of the opposite charges. Now, since electrons can be lost or gained, meaning if I rub a material against another one, electrons can be lost by friction, then the proton number is actually what we use to determine what an element is. So since it always remains the same for a given atom, then we must use the proton number instead of the electrons to determine what that element is. Now, if two atoms have the same number of protons, they are indeed the same element. So sometimes two atoms have the same number of protons, but they have a different mass number. In this case, we refer to these as isotopes. So isotopes are the same element, they have the same proton number, but they have different mass numbers. All right, so let us now jump into radiation. Nuclear radiation or radioactivity happens because the nucleus of an atom is unstable. Because of this, it will change into a different nucleus by giving out radiation to achieve a stable state. And experiments have shown that there are three types of radiation: alpha, beta, and gamma. Now, what happens is that when an atom is in an unstable state, it needs to release some of the energy in order to achieve back a stable form. Now, how it will do this is either by emitting an alpha, beta, or an alpha or beta particle, or it may emit gamma radiation. So a nucleus may change to a different nucleus by emitting one of these three types of radiation. An alpha particle is a helium nucleus, a beta particle is a fast-moving electron, and gamma is not an actual particle, it is just high amounts of energy that is being released from an atom. Now, you might be wondering if external factors can affect radiation, and it cannot. So radiation is basically dependent on the internal structure of the nucleus. So if I have too much energy, I need to release that. And you can think of that in the form of maybe a child that's had too much candy. If I have too much candy, then I need to release that energy by playing. And so you can consider alpha, beta, and gamma as a type of playing where I release that energy and I now achieve a stable state. All right, so during the formation of the Earth, nearly 4.6 billion years ago, radioactive minerals became a small but significant part of the Earth's crust. And today, these minerals can be found naturally in the environment, in rocks, in soil, in water. So radioactive minerals exist in most countries around the world. So let's examine the characteristics of nuclear radiation. We're going to look at alpha, beta, and gamma. So alpha, as we would have mentioned before, is a helium nucleus consistent of 2 protons and 2 neutrons. A beta particle is simply a high-speed electron, and gamma radiation is simply the emission of electromagnetic energy. Now, we can look at them, or we can differentiate between them by looking at how far can they go in a range in terms of through the air, or in terms of how far can they penetrate the tissue of the human body. So we're looking at this column here where it says range in tissue. Alpha particles cannot penetrate the epidermis of the skin. That's the first layer of your skin. So your first layer of skin can actually block the penetration of alpha particles. Now, beta particles can actually penetrate through several layers of your skin, and gamma radiation is very penetrating, but it is dependent upon the amount of energy that it starts off with. So the further you are away from gamma radiation, the safer you are. But if you do come in contact with it, then it is actually very close to being lethal. All right, so the next thing we're going to be looking at is the sources of these different types of radiation. Now, alpha particles can actually be found from uranium and plutonium. Beta particles are usually the decay of fission products and neutron-induced elements. And gamma radiation, they're usually products of neutron-induced elements also. Moving on to the next slide. Now, some materials that these types of radiation can penetrate through, we have alpha particles that can be stopped by a thin sheet of paper. Beta particles can penetrate through a thin sheet of paper, but they're stopped by a thick enough piece of aluminum. And gamma radiation can usually only be stopped by thick pieces of lead. Okay, so if we are trying to differentiate between alpha, beta, and gamma, there are a few things that we need to know about their track patterns. Now, alpha particles produce thick, straight tracks when they're put inside a cloud chamber. And the reason for this is because the mass of the alpha particles is pretty high, it's pretty heavy. So you can just imagine that if I were a bigger person in terms of my body mass and I was trying to maneuver my way through a room, then most of the people would just move out of the way and allow me to pass through undisturbed. So the straight tracks of the alpha particle are because they have a high enough mass so as to move all the different particles of air from out the way. Beta particles, however, will produce thin, twisted tracks. These are because they're fairly light in terms of their mass, and so the different obstructions inside the air would cause them to go off track. So the tracks are thin because of their low ionizing ability, and they're twisted because of their very small mass, making them easy to deflect. Gamma rays produce very thin, short, scattered tracks. And this is because they have a very weak ionizing ability. So they kind of just bounce around on the different particles in the air. Because remember, it's just high speed moving energy. All right, so we're gonna look at a few examples of alpha decay. Now remember we said that alpha is actually a helium nucleus consistent of 2 protons and 2 neutrons. So here we have an alpha particle that is being emitted from uranium. Now, remember the reason that we said that a particle would undergo radioactivity or radioactive emission is because it's seeking to let loose some of the energy and achieve a stable form. And so it would have decayed into this new element or a daughter nucleus referred to as thorium. So if we look at the equation at the top here, we would have realized that the mass number has actually decreased by 4. So we started off with uranium 238, we decayed, let off an alpha particle, and we have now reduced our mass number to 234. Now, if I add up all the mass numbers on the right-hand side of the equation, I should get back the exact same number as on the left-hand side. So my original element should give me the same amount of mass as my products of elements. Now, if we look here and we examine the proton number, we would have realized that the proton number has also decreased by 2. And that is because the alpha particle has a proton number of 2, which means that my daughter nucleus would have a proton number of 90 coming from 92. All right. So now that we are finished with alpha, let us have a look at beta decay. So remember we said that beta decay is actually just a form of a high-speed moving electron. So what that means is that my product will have decreased in terms of its mass number, in terms of its proton number. Now we have 2 different types of beta decay. We have positive beta decay and negative beta decay. So when I'm looking at beta decay, my mass number should remain unchanged, but my proton number should either increase or decrease dependent on if it is a positron being released or if it is an electron being released. Now, what do I mean by a positron? A positron is simply an electron that actually has a proton number of 1. All right, so let's look at the first equation here. We have the mass number remaining unchanged because remember the electron basically has a mass of 0. So the mass number would remain unchanged. However, the proton number down here would have actually increased by 1. And in this case, it would have decreased by 1 because here we have a positron where the proton number is a positive 1. And here we have a negative 1 because it is an electron, and so it would have increased. All right, we're going to move on to gamma decay. Now, unlike alpha and beta decay, the parent nucleus does not undergo any physical change, meaning that the mass number nor the proton number would change in this process. So a daughter and a parent nuclei are the same. Most of the time, gamma decay occurs after the radioactive nuclei have already undergone alpha or beta decay, meaning that after I emit an alpha particle or a beta particle can be either an electron or a positron, then I would have also released some amount of electromagnetic radiation, which would be the gamma decay. So the alpha and beta decay leave the daughter nuclei in an excited state, and from the excited state, the daughter nuclei can get back to the ground state by emitting one or more energy gamma rays. So if we examine the diagram here, we'd realize that the energy levels are actually decreasing after each different type of decay to achieve a stable form. Now, the last thing that we'll be looking at today is half-life. When a radioactive substance decays, it is actually impossible to tell when a particular atom will break apart and push out a beta or an alpha particle. Now, the reason for this is because it is a random and spontaneous process. Remember, we said that external elements cannot affect radioactive decay. But what we can determine, however, is a phenomenon known as half-life. When a large amount of atoms of the same type are put into one place, we observe that within a certain amount of time, the same amount will actually continue to decay. And so if we look at this, we're going to say that an element takes 10 years to decay, and we're going to call that element limestone. Then after 20 years, we should have 7.5 grams remaining. So let's say that we start off with 30 grams of that element. After 10 years, we should have 15 grams. After 20 years, we should have 7.5 grams. After 30 years, we should have 3.75 and so on. Now, do realize that each time one period is experienced, the amount of the element that remains is half of the original amount. And so we refer to half-life as the time required for a quantity to reduce to half of its initial value. Now, this term is used to describe how quickly unstable atoms undergo or how long stable atoms survive radioactive decay. So let's just go through this one more time. We're going to say that the substance is limestone and it takes 10 years for that specific substance to decay or to reach the half of its original amount. If we start off with 30 grams, then after the first set of 10 years, then we should have half of the original amount, which is 15 grams. After 20 years, which is 2 sets of half-lives, then we should have half of the 15 grams, which is 7.5 grams, and so on and so forth. Now, the symbol for half-life is T with a subscript half written below it, as you see here. All right, so we're just going to look at a graph of the half-life of a substance. Now, whenever we look at a graph and we realize there's a very steep curve, we refer to this as exponential decay. Now, what that means is that it's a very rapid rate of decrease. So after every one set of half-lives, I would have decreased to half my original amount, which is actually a very fast rate to decay at, even if we were talking about millions of years. So let us say that my atom or my set of species of atoms takes 1 million years to decay to half of its original amount. Then after 2 million years, I would only have 1/4 of that original amount. And so we refer to this exponential decay as a very fast or rapid rate of decay. And so most of your half-life graphs would look something like this. Sometimes you might see the graph saying activity instead of half-life. They should have the same curvature as we see here. All right, so this brings us to the end of this presentation, and we are just gonna jump into some questions that are related to this presentation. Right. Okay, so here we are. So we are starting with the question. So it says, half-life is defined as, and so we would have just ran through that. Half-life is the time that it takes a set of radioactive atoms to decay to half of its original amount. And so the answer here would actually be A, the time it takes half of the radioactive samples to decay. All right, so it says, which of the following scientists discovered the relationship E is equal to mc squared? And the answer for this would be Sir Albert Einstein. All right, which of the following cannot be deflected by a magnetic field? Now we would have examined all the different types of radiation in the table before, and so we realized that the answer is C, gamma rays. Remember that gamma cannot be deflected unless we have a very thick piece of lead. All right, so nuclide representation, this question is going to be referring to that. It says the nuclide thorium-23490 contains, and it wants you to tell them how many protons and how many neutrons are there. Remember that the top number is our mass number and the bottom number is our proton number. And so in order to find how many neutrons are there, we would actually have to minus this proton number from the mass number, giving us the answer of C. 90 protons and 144 neutrons. All right. Which of the following statements about radioactive decay are correct? It is a random process. It is dependent on conditions external to the nucleus. It is due to changes of the nuclei of atoms. Remember we said that radioactivity is not dependent on any external factors, and so we realize that our answer would have to be B, 1 and 3 only. Okay, so it says N0 radioactive nuclei are present in a sample at time t equals 0. Which of the following graphs best represents the variation with time of the number n of undecayed nuclei present? Now remember that we said that graphs of radioactive nuclei are usually represented by exponential decay, and so the answer would have to be D. Isotopes of an element differ from each other in that they have different, and yes, that answer would be the number of neutrons. Remember that isotopes of an element have the same proton number, but they have a different mass number. And so that must mean that the number of neutrons differs. All right, so it says, which of the following graphs shows how the variation, okay, this one is similar to the first one, and so the graph of radioactive decay is exponential decay. So notice here it says activity, which would be the difference between the first one, but the answer is still D, showing our exponential curve. According to the Rutherford-Bohr model of a neutral stable atom, if n is the number of protons, n is the number of neutrons, P is the number of protons, and E is the number of electrons in the atom, then for all elements, remember we said that if we are in a neutral stable state, then the number of protons must equal to the number of electrons. That is, the set of positive charges must cancel out the set of negative charges, and so the answer would be B. All right, which of the following symbols would be possible for an isotope of a nuclide represented by XAZ? Now remember we said that isotopes of an element have the same proton number, but they might have different mass numbers. And so if we look at the options that are given here, A has a different proton number than the original question. B is also shoving the proton number, and C is doing the same thing. And so D, we realize, has the same proton number but a different mass number, and so that has to be the answer, D. So it says sodium 24 decays into magnesium 24, with the emission of a beta particle and can be represented by the following equation. Which of the following particles should be placed in the box to complete the equation? Now, remember we said earlier that whatever is on my right-hand side of the equation must add back to give me back what is on my left-hand side. And so if we look here, we have a proton number of 12 on the right-hand side, but 11 on the left-hand side. And so we need to fill in the box with a number that when I add them together, I get back what is on the left-hand side. And so I realized that my answer must be A, because 12 take away 1 would give me back 11. Okay, which of the following statements about radioisotopes is true? Now, these answers are a bit different. So they're saying they are not used in scientific work because they are too dangerous. Now, radioactive isotopes are indeed dangerous, but we have to be mindful of some of these trick questions, right? Earlier, we would have said that radioactivity is commonly used in medicine in terms of we use them for cancer research and we use them in terms of x-rays. So the answer here would have to be C. It says they are sometimes used in medicine. All right, so don't be fooled whenever they're putting close answers there. It says that they are not used in scientific work any at all because they're too dangerous, which is not true. So the answer would have to be C. So item 55 refers to the diagram below, which shows, sorry about that. Okay, so it says, which of the following statements is or are correct? 1, the mass or the nuclear number is 11, the atomic or the proton number is 5, and 3, the atom shown in the diagram is positively charged. Now, how we determine if an atom is positively or negatively charged is we would add up the number of electrons, add the number of protons, and see whether or not they cancel each other. If we have a remainder of electrons, that would mean that it's negatively charged. If we have a remainder of protons, that would mean that it's positively charged. So we'll go ahead and look inside the nucleus here, and we have 1, 2, 3, 4, 5 positive charges, and 1, 2, 3, 4, 5, 6 neutrons. Looking at the outside, we have 1, 2, 3, 4, 5 negative charges. And so we realize that the number of protons is actually equal to the number of electrons. So looking at this answer here, the answer would need to be C, 1 and 2 only. So the mass or the nuclear number is 11, because if we add up everything inside the nucleus here, we do get 11. And it also says 2, the atomic or the proton number is 5, because when we added the protons, we did indeed get 5. 1, 2, 3, 4, 5. All right, so it says, according to the Rutherford-Bohr model, if an atom has a neutral state, then the number of protons must be equal to the number of electrons. And so we have the answer there being B. An isotope of zinc has a nuclide which can be represented by Zn6430. The number of electrons in a neutral atom is, so we're going to look at this very closely. We have the mass number being 64 and the proton number being 30. Remember that from the Rutherford-Bohr model, we realized that if something is to be neutral, it must have an equal number of protons as it does neutrons. And so since they have given us the proton number here in the question, then the number of electrons must be equal to that number, and the answer would be A. Which of the following would be possible symbols for an isotope of a nucleus represented by X, AZ? Now remember we said about isotopes, they must have the same proton number, but they may have different mass numbers. And so we look at the options that are given here and realize that only 1 and 3 have the same proton number, and so the answer must be D. Okay, so which of the following is the definition for the term half-life of a radioactive nuclei? So the time taken for the activity of any sample to fall to half of its original value, the time taken for half of the nuclei present in any given sample to decay, or 3, half the average number of disintegrations per second. And so the answer here is 1 and 2 only. In the equation, delta E is equal to delta M times C squared. We have the answers. So what they want you to do is to tell them the definition of each one of these terms inside of the equation. And so we realized that E represents the energy, M represents a change in mass because we have delta there, and C represents the speed of light squared. So the answer here must be B because we have that delta M is equal to the mass loss. Now you might be wondering why the answer isn't A. That is because we have a delta there. So delta means that my mass must have changed. It must have either lost some mass or gained some mass. In this case, it would have lost. And so the answer would be B. All right, so here is where we end our presentation today. And I do thank you for tuning in, and I hope that you have learned quite the wealth of knowledge today. And I was super excited to have you. And
remember to subscribe.
Remember to like
this video, subscribe, and leave your comments. Miss McLeod will be more than happy to respond. Remember to visit our website, www.stembuildersjm.com.
All right, so it was great having you guys, and all the best in your exam.